So question is 30 and we have to find out the correct order with increasing bond length in KO2, O2, O2, ASF6. Potassium is positive, so this is negative. This is molecular oxygen, and this one obviously here it is positive because this is negative, right? Bond order, how is it related to bond length? It is inversely proportional. So if we calculate bond order, we can comment on bond length. Okay. So to find out the bond order, we have to use molecular orbital diagram of oxygen. And for that case, what we will do, we will write the atomic orbitals for the oxygen. So this is atomic orbital for oxygen on both sides. The MO will come in between. And this is say for the 2p. So when two atomic orbitals combine, they will be forming a bonding and an anti-bonding. Bonding will be lower in energy. Anti-bonding will be higher in energy. As simple as that. Two atomic orbitals combining will produce two molecular orbitals. Okay, that is the principle one has to remember. So for 1s, this is for 2s. Okay, and this is the 2p. This is the energy of the atomic orbitals, and so is the energy of the molecular orbitals. Now 2pz, when it combines along the intermolecular axis, internuclear axis. So it is going to form the sigma orbitals, and this is sigma 2p z. This is sigma 2p sigma star 2p z. This is sigma 1s. This is sigma star 1s. Star indicates antibonding. Without the star, it is bonding. This is sigma 2s. This is sigma star 2s. Now the other px and py, when they combine, they form pi orbitals, and they are of the same energy, like this. Okay, and the above one is, these ones are anti-bonding, the below ones are bonding. Oxygen is a total 16 electron system, right? So we will fill up by filling up the lower levels first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Now this level will get cancelled with this one. This one is get cancelled with this one. So we'll only consider electrons over here. Okay, the below ones we don't need to consider for calculation of bond order. So say we are saying bond order of O2. Now with respect to this level and that level, the ones that are lying below are the bonding, and this one is the anti-bonding. Keep that in mind just. So we can see over here there are 6 bonding electrons and 2 anti-bonding electrons. So obviously the bond order is over here too. Now if you remove one electron, you will generate O2 plus, right? So that is 6 minus 1 divided by 2, and we will say it is 2.5. This is the original diagram for oxygen. Now if you add one electron, obviously in this level, we will get a bond order for O2 minus, which is obviously we will say 6 here bonding, 3 here anti-bonding. So 6 minus 3, and that should be equal to 1.5. So we now know the bond order for all the species. Okay, and if we arrange them, then we will say O2 plus greater than O2 greater than O2 minus. This is bond order. The reverse of this will be bond length order. Now, since they have given here, let's write it and then we'll compare. So we will say this is more than that, which is more than that. Okay. Now, if we compare with the answers or options given, we will say this is the correct option. Okay. Question number 31, it says geometry and bond angle of SO3 2 minus. So for that, we will do total valence electron count, 6 for sulfur, 6 for oxygen. There are 3 such and 2 electrons, and that gives me a total count of over here 26 electrons. Okay. Now 26 is a number that is greater than 8, so we will say 26 divided by 8, and we will say 3. This is indicating bond pairs. Number is 2, so we divide by 2, and that gets cancelled. So this is indicating lone pairs. So in total, we will say there are 4 electron pairs, and this is our steric number. So obviously this is having sp3 hybridization, that is for sure. Alright, and for sp3 hybridization we know the bond angles are close to 109. Okay, now if we draw the structure of this molecule, we will find that there is one lone pair and there is one oxygen with a minus charge, another one with a minus charge. For the other oxygen, we will make a double bond over here. Now, since there is a bond pair lone pair repulsion, this angle over here cannot be equal to 109 degrees, ideally found for a tetrahedral system. Okay, so this is basically going to be lower, all right, than this, and somewhere we will say it is similar to 107. Now, since there are only 3 bond pairs, okay, and only one lone pair, so for that we will, for the structure, we will neglect the lone pair or not consider the lone pair. So without considering the lone pair, this particular molecule will be having a structure which is pyramidal. Okay, so the geometry over here we will say is pyramidal, and the bond angle will be around 107. Okay, that should be our correct answer over here. Question here is in 32, in which of the following pairs both the ions are colored? Okay, so for the ions to be colored, they should not be D0 or D10 system. As we can see over here, scandium is a D0 system, so this option is wrong. For copper 1 plus, we know it is a D10 system, so this option is wrong. Again over here we have scandium, which is a D0 system, so this is wrong. By neglecting or finding out the incorrect options, also we can reach out the correct option. This is a D1 system, and that one is a D8 system, the nickel 2. So the correct answer over here is going to be option A.